picture this. You've finally decided to take that complex multi-city vacation you've been dreaming about.
Oh yeah, the big one.
Right, the big one. So you sit down, pull up your favorite AI assistant, and ask it to plan the whole thing.
Mm.
You want specific hotels, certain flights, highly rated restaurants, the works. And within seconds, it spits out an initial itinerary that looks absolutely brilliant.
It always looks amazing at first glance.
It really does.
Yeah.
I mean, you feel like you're living in the future, but then it actually tries to execute the tool calls to book it all.
Yeah, that's where the magic usually fades.
Exactly. Suddenly, it schedules you to visit a museum 2 hours before it opens, or it books you into a hotel way outside your budget. Or worse, it puts you on the completely wrong airline.
Right.
It's incredibly frustrating. Why do AI agents look so incredibly smart at the planning stage, but, completely fall apart in the follow-through?
Well, it's honestly the defining problem of autonomous AI right now. I mean, we expect these models to act like seasoned travel agents or project managers.
Yeah, we really do.
But their operational awareness is just so brittle once they start interacting with the actual friction of the real world.
Right, because the real world is messy.
Exactly. Generating a block of text is fundamentally different from navigating a live booking API that might, throw unexpected errors.
Okay, let's unpack this. Because to fix a broken AI agent, we first have to understand the specific anatomy of its failure.
Absolutely.
What is actually going wrong under the hood? Our mission today is to give you, the listener, a shortcut to staying well-informed on the absolute cutting edge of how we solve that execution gap.
It's a huge topic.
It really is. So we are doing a deep dive into a brand new, highly foundational preprint paper from researchers at Amazon. It's titled PV Up, Bridging Planning and Execution in LLM Agents via Trajectory Refinement.
Yeah, and the central problem the Amazon researchers identify here is what they call plan execution misalignment.
Okay, break that down for us.
Well, in a vacuum, the logic of an AI's initial plan is usually pretty sound. But the real world, or even just a digital environment like a live database, is highly dynamic.
Right.
So the agent starts executing its plan, and it immediately hits a snag. Like a website is down, a specific flight is sold out, or some constraint just changes.
Basically, the environment doesn't perfectly match the pristine assumptions the AI made at step one.
Exactly. And that mismatch creates this compounding effect. If you look at standard agent frameworks like ReACT, which is the baseline most developers use right now, they operate in a very localized loop.
ReACT meaning reasoning and acting, right?
Yeah, reasoning and acting. So it has a thought, takes an action, and observes the result. If something goes wrong, it just tries to apply a quick Band-Aid to that specific local step.
Oh, I see, like a quick patch.
Right. It might tweak the prompt right at the moment of failure, but it doesn't optimize what researchers call the full trajectory.
Full trajectory.
Yeah, the entire continuous path from the agent's very first thought to its final executed action. So the agent pushes forward, patching holes, ignoring the cascading reality of the execution.
Wow.
And eventually, the whole plan just becomes unrecoverable.
It's like someone confidently following a printed MapQuest route from 2005.
That is a great way to put it.
Right. They are driving along and they plunge straight into a newly built lake because they're absolutely refusing to look at the actual road in front of them.
Because the paper told them to go straight.
Exactly. The printout said go straight, so they go straight.
Huh.
So if the AI can't see the road, how do we give it eyes?
Well, we don't just need to give the AI eyes to see the lake. We have to give it a completely new operational framework.
Okay.
It needs to know how to systematically reroute itself when it spots the water. And that is what the PVOT framework does.
P58, right.
PVOT treats the entire trajectory as an optimizable object, rather than just a static script to be executed blindly step by step.
And PVOT stands for Plan, Inspect, Evolve Trajectories.
That's right.
The researchers actually outline this using a really vivid 4-stage analogy in the paper's appendix that makes the mechanics so clear. They compare the AI agent to a head chef in a high-end restaurant kitchen.
It's a brilliant analogy, because running a kitchen requires both rigorous upfront planning and constant real-time adaptation.
Right.
So the first stage of PFIT is plan. Before the AI is allowed to touch any external tools, like a web search or a live booking API, it has to generate a highly structured plan.
Like a chef writing the menu and prepping the station.
Exactly, before the dinner service even begins.
So it's not just jumping into the deep end and hoping for the best.
No, not at all.
The PFIT framework forces the AI to explicitly state its goals, list the specific tools it's going to use, map out the dependencies between steps, and this seems crucial, plan out failure contingencies before it even starts.
Yeah, that part is huge. It forces the agent to establish a baseline of intent. I mean, if you don't know what you are trying to achieve, you can't measure if you are actually failing.
Right, you're just guessing.
Exactly. Which leads to the second stage. Inspect. This is periodic reflection.
Okay.
Imagine our chef tasting the sauces mid-service. They don't wait until the food is plated and served to the customer to realize it lacks salt.
That would be a disaster.
Right. So P-Vivo injects reflection checkpoints automatically during execution. It actively scans for discrepancies between the original plan and what the external tools are actually returning.
Which catches those MapQuest into the lake moments nice and early.
Exactly.
Then we hit the third stage, Evolve-E. This is the adaptive plan revision. Let's say our chef realizes a key ingredient, like the fish has spoiled.
A bad AI agent using standard RIAS-CT would just keep trying to cook the rotten fish.
Oh.
Or he would try to order more fish from a closed market over and over again in this massive loop.
Oh man, that retry loop is one of the most notorious failure modes for AI agents today.
It really is.
They just keep hammering the same failed web search query, racking up compute costs.
Evolve breaks that loop. If an approach fails, the AI must diagnose the root cause and propose a fundamentally different strategic path.
So swapping the fish for chicken, basically.
Right. And to your point about loops, the researchers put a strict 3-invocation cap on this Evolve stage.
Oh, smart.
Very. If the AI tries 3 entirely different approaches and still fails, it doesn't get stuck infinitely. It gracefully degrades and constructs the best partial answer it can.
And finally, the fourth stage is verify, the final quality gate. The chef is standing at the pass, checking the plating, making sure the dietary restrictions were honored before the waiter takes it to the dining room.
Spot on.
The AI has to reread your original prompt and explicitly check its final answer against every single constraint you gave it.
Exactly.
But wait, I have to push back here. I mean, I'm looking at this 4-step process,
Yeah.
and it just sounds like prompting the AI to think harder or double-check its work.
I get why it sounds like that.
We've been telling ChatGPT to do that for years. What makes Pivot fundamentally different from just adding, take a deep breath and check your work to a system prompt?
Well, it's a fundamental architectural shift in how the system learns from its mistakes during inference. Pivot isn't just asking for a second opinion. It's performing trajectory-level optimization using a monotonic acceptance rule.
Wait, monotonic acceptance? You're losing me.
I know it's a mouthful.
Are we talking about the AI actually grading its own homework with the math formula?
In a sense, yes. When the Evolve stage proposes a new path, say, swapping the spoiled fish for chicken, the system doesn't just blindly accept it and move on.
Okay.
It evaluates the new trajectory against the old one, using a specific objective function. It estimates the trajectory loss.
The trajectory loss.
Yeah, basically calculating how far off the path to the final goal the agent actually is. The monotonic acceptance rule dictates that the system will only accept the updated plan if it mathematically improves that loss score.
Oh, wow.
Yeah, it's a rigorous, gradient-like optimization over the plan itself. The new path has to be provably less broken than the old one.
Here's where it gets really interesting, because you just mentioned trajectory loss and gradient-like optimization. That sounds like heavy neural network math. But we are talking about a language model that processes discrete text tokens. How does Piva actually optimize these plans without traditional math?
You've hit on the core technical innovation of the entire paper right there.
Okay.
In traditional machine learning, you train a model using backpropagation. You calculate the error at the end, find the exact mathematical derivative of that error, and propagate it backward through the network to adjust the weights.
Right, the standard deep learning stuff.
Exactly. But language trajectories, like the steps an AI takes to plan your trip, are discrete words and actions. They aren't continuous numbers.
So you can't really do the math on them.
Right, you can't run traditional backpropagation on them because they are non-differentiable.
Because you can't find the mathematical derivative of the word hotel.
Exactly. So Pivot introduces a concept called textual gradients.
Textual gradients.
It uses structured natural language feedback as a surrogate for that mathematical gradient. When the inspect stage detects a failure, it doesn't just say, "This is wrong, try again."
What does it do?
It works backward from the failure outcome to find the very first causal break in the chain of events.
Okay, it's like a detective tracing a ruined cake backward. The final product on the counter is a complete disaster.
A total mess.
Right. But the cake isn't ruined because the oven is broken, and it isn't ruined because the frosting is bad. It's ruined because way back at step 2 of the recipe, you grabbed the salt instead of the sugar.
Yes.
Everything after step 2 was doomed. So Pivot uses text to trace the failure all the way back and finds the salt.
That is exactly it. It finds the salt. That backward attribution signal is formatted directly into the prompt.
Interesting.
The model explicitly identifies the failure node, maps the causal chain that led to the error, and formulates a correction strategy. And this mechanism is where Pivot achieves its incredible efficiency.
How efficient are we talking?
Well, the paper highlights that Pivot requires 3 to 5 times fewer tokens than competing refinement methods like self-critique or agent debug.
Wow, 3 to 5 times fewer tokens is a massive compute saving for anyone running these models at scale. How is it pulling that off?
Let's look at the baselines. If you use a method like agent debug, the system maintains a running memory of its past mistakes. If you use self-critique, the model generates an entire output and then reads it back to look for flaws. In both cases, the AI is forced to reread the entire massive transcript of its past failures every single time it tries to correct itself.
Which eats up an enormous amount of context window.
Precisely. Pivot surgically edits the trajectory tree instead.
Meaning, once it finds the salt, the exact step where things went wrong, how much does it actually cut?
It preserves everything that happened before that step. It keeps what they call the validated prefix, the good part of the plan.
Oh, that makes sense.
It only rewrites the unsupported suffix, the bad part of the plan moving forward. The model isn't forced to reprocess the successful steps.
It just prunes the dead branch of the decision tree and grows a new one from the exact point of failure.
Exactly.
So it doesn't throw the baby out with the bathwater. That solves the token bloat problem beautifully.
Okay, textual gradients sound great in theory, but when you put this up against chaotic, open internet benchmarks, does that backward tracing actually hold up without a human holding its hand? The benchmark results are actually pretty striking. They tested PIWA on 2 major suites.
Okay.
First is deep planning, which tests long horizon constraint satisfaction, so travel and shopping tasks that require maintaining context over dozens of steps.
Complex stuff.
Very. And the second is GAIA. GAIA is a brutally difficult benchmark designed to test multi-step reasoning and open domain tool use. It actively tries to trip the agent up with messy, real-world data retrieval.
So the Wild West of the internet.
Right. And when Pivot was given human-in-the-loop feedback, meaning a human was validating those textual gradients, it hit up to a 94% relative improvement in constraint satisfaction on deep planning compared to the baseline models.
Wait, 94% relative improvement?
Yeah.
That completely changes the usability of the agent?
It really does. But what stands out even more is that in its fully autonomous variant, where the system acts as its own judge without any human intervention, it still crushed standard baseline architectures.
Incredible. The paper includes some really vivid step-by-step examples of this in action.
Oh, the examples are great.
Yeah, there's one case called the Canyon Flavor Restaurant Failure. The user explicitly asked the AI to include this specific restaurant in a travel itinerary.
Right.
The baseline AI searched for Canyon Flavor Restaurant, the search tool returned a not found error, and the baseline AI just gave up.
Just threw its hands up.
Literally failed the entire multi-day trip because of that one missing piece of data.
Exactly.
But when Pivot ran the same task, it hit that failure, diagnosed the root cause in the inspect stage, and evolved its strategy.
Right, it pivoted.
Right. It recognized the exact name might be slightly off in the database, so it instructed its search tool to look for aliases and location-based alternatives. It found the restaurant under a slightly different name and successfully finished the plan.
It demonstrated genuine operational resilience. And there was another fantastic example that highlights the verify stage on a complex trip from Harbin to Beijing.
Oh, the flight one.
Yes. The user had 3 travelers, needed specific hotel ratings, but crucially, requested the absolute cheapest Airbus flight.
Airbus specifically.
Right. The baseline AI gathered all the flight data, but completely ignored the aircraft manufacturer constraint. It booked a cheaper Boeing flight instead.
It gathered all the right data, but just totally failed to synthesize the actual constraint.
This happens constantly in long context windows.
Right.
The model's attention degrades, but Pivot caught the exact moment that constraint was violated during its final verify stage.
Awesome.
It cross-referenced the selected Boeing flight against the user's initial prompt, flagged the manufacturer violation, traced it back to the exact tool call where the flight was selected, and rebuilt just that final leg of the plan to select the correct Airbus flight.
This is wild to me because right now the entire AI industry is obsessed with OpenAI's O1 model and this concept of giving agents massive inference compute to think long.
Oh, the thinking budget hype.
Yes. The prevailing wisdom seems to be just give these frontier models a huge thinking budget, let the model generate 10,000 tokens of internal monologue, and it will figure this out on its own. Are the Amazon researchers saying that throwing raw compute at the problem is basically useless if you don't structure the reflection?
They ran an ablation study to test exactly that hypothesis.
Really?
Yeah. They artificially increased the extended thinking budget on the baseline models, giving them massive room to generate internal monologue. And the data from that study is a complete myth buster.
What did it show?
Giving an AI more unstructured thinking tokens didn't improve performance on these long horizon tasks at all.
Why wouldn't it? I mean, if the model has way more time to process the problem, shouldn't the plans naturally get better?
You would assume so, but the data showed a massive distributional flaw. In a standard agent setup, nearly 100% of the thinking happens at step 1.
Wait, at the very beginning?
Yes. The model spends all its allotted thinking tokens decomposing the task and pontificating about strategy right at the very beginning, before it has interacted with any tools. But when it actually comes time to synthesize the 20 different tool outputs it just gathered into a coherent final answer, 99.2% of the final plan generation steps produced 0 thinking tokens.
Wait, 0. Literally 0.
0.
So it does all this deep philosophical planning before it has any concrete facts, and then once it actually pulls the facts from the web, it just blindly assembles them without reflecting on them at all.
Exactly that. It's a pacing problem. Pivot works so well not because it forces the AI to think more overall, but because it forces the AI to think in the right places.
Oh, that is so clever.
By injecting the inspect and verify stages, it places the cognitive load precisely where it matters most. At the synthesis stage, right before the final answer is given, when the agent actually has the real-world data in front of it.
That makes total sense. You wouldn't want your chef spending 3 hours planning a menu and then plating the food with their eyes closed. Pivot paces the cognitive load. So this framework is clearly a massive leap forward for agent reliability. But we need to look at the boundaries here. If we take textual gradients and this trajectory editing tree into the real world, what are the actual limitations?
Well, the paper is very transparent about where Pivot hits a wall.
Okay.
First, despite being token efficient by pruning that unsupported suffix, it is still fundamentally bound by the model's finite context window.
Right, the memory limits.
Yeah. As a task drags on over dozens and dozens of steps, the earliest instructions can suffer from context degradation. The agent can still lose the thread of the original goal if the context gets stretched too thin.
And what about that GAIA benchmark?
Yeah.
You mentioned earlier that it relies heavily on open web search.
What?
Does the chaotic nature of the internet break the trajectory?
On GAIA, Pivot's improvements were solid, but they were bottlenecked by retrieval quality.
Meaning what exactly?
Meaning, if the underlying search tool simply cannot find the information on the internet, PIDS can't magically manifest it. You can optimize a trajectory all day long, but if the required data simply doesn't exist in the environment, the agent will still fail.
You can't cook a meal if the grocery store is completely empty.
Exactly. If we connect this to the bigger picture, though, the societal implications of solving execution misalignment are profound.
How so?
Highly reliable autonomous systems democratize incredible capabilities. You suddenly have access to an expert-level planner, researcher, or software engineer that actually follows through, adapts to errors, and meticulously checks its work before handing it back to you.
But the more reliable they get, the more we lean on them.
Which introduces serious secondary risks. As these systems stop failing in obvious, clumsy ways, human oversight naturally decreases. We start trusting them implicitly to execute complex financial, logistical, or administrative workflows.
The blind trust factor.
Right. And that misplaced trust, combined with inevitable labor displacement as agents take over multi-step knowledge work, means we are entering a phase where the dual-use potential of this tech by bad actors becomes much more viable.
Yeah, that's a scary thought.
A highly capable agent that can adaptively overcome obstacles is a powerful tool, regardless of whether the goal is planning a vacation or mapping a network vulnerability.
To ground this directly for you listening, the next time you are using an AI agent for a complex task at work, Maybe you are having it compile a massive research report or schedule a convoluted logistics chain and it gets stuck in a repetitive loop. You'll now understand exactly why.
Because it's stuck in that rigid script.
Exactly. It's executing a rigid, localized script. And you'll know that the secret to unlocking its potential isn't just throwing more raw compute at it or telling it to try harder.
No, not at all.
It's forcing it to pause, diagnose the root cause of the failure, adapt its strategy, and meticulously verify its output against your original constraints.
Moving from an execution mindset to an optimization mindset.
So what does this all mean? To wrap this up, treating an AI's plan as a living, editable trajectory rather than a rigid set of instructions is clearly the future of autonomous agents.
Absolutely.
PV proves that if you give an AI the framework to reflect, adapt, and mathematically prove its corrections using textual gradients, it stops being a clumsy intern and starts acting like a resilient expert.
I want to leave you with one final thing to mull over, drawn directly from the paper's data.
Oh, let's hear it.
When the researchers analyzed the backward error traces from the baseline models, they found something deeply surprising. The most common cause of failure wasn't that the AI was missing information.
Really? What was it?
The most common failure was ignored information.
Ignored.
Yeah. The agent successfully gathered the correct data using its tools, but failed to synthesize it at the crucial moment because its thinking budget was allocated entirely at the beginning of the project.
Right, the 99% at step one.
Exactly. If AI agents fail, mostly because they lack structured reflection at the end of a process, rather than lacking raw data, well, how often do human organizations fail for the exact same reason?
Oh, wow.
We gather mountains of data, we hold endless planning meetings, but we fail to pause, verify, and adapt right before we execute the final product. Could studying AI trajectory refinement actually give us a blueprint for fixing broken corporate decision-making?
Now, that is a fascinating question to leave off on. If your team is failing to execute, maybe you don't need more data. Maybe you just need to structure your reflection. A massive thank you to you for joining us on this deep dive into the state of the art of Gen AI. Until next time, keep questioning, keep learning, and we'll catch you on the next one.